Cosmic voids are the darkest places in the universe. They're like great deserts, and astronomers have found something there, a subtle order, an undeniable structure within all that emptiness. These vast nothings are essential to everything. There's a blueprint in a region defined by absence. Faint galaxies are spinning in sync. That tells us something about the forces that shaped reality. It means finding meaning in the void. The universe is built like a sponge, a cosmic sponge. It's not a random scatter of stars, it's this intricate, three-dimensional web. The bright threads of that web are galaxy filaments, these immense chains of star clusters and glowing matter. And where the threads cross, you get the dense knots. Galaxy clusters, the universe's great cities, and in between those radiant structures stretching for unimaginable distances are the voids, dark, bubble-like cavities. They make up most of the space in the cosmos. They're the universe's deserts. To understand the order inside them, you have to grasp what a void is. A cosmic void isn't a perfect emptiness. It's a region with an extremely low density of luminous matter. The bright galaxies we can easily see. Think of it like a vast, sparsely populated countryside. And then you have the bustling metropolis of a galaxy cluster. Cosmologists see voids as fundamental. Rien van de Wegeert describes them as the universe's infrastructure. They're not just leftover spaces. They are the dominant architecture. They occupy the overwhelming majority of cosmic volume. As gravity pulled matter into the web over billions of years, it left behind these underdense regions. The scale is hard to comprehend. A typical void can span 100 million light-years or more. They come in different sizes, from smaller mini-voids to staggering supervoids. And these places become ideal, quiet laboratories. Without the bright glare and chaotic gravity of dense clusters, you can observe subtler cosmic effects. You see with clearer vision. One of the most famous is the Boötes void, discovered in the 1980s. It's so vast and so seemingly empty that early observations called it the Great Nothing. Finding it was a profound shock, a mystery that asked a fundamental question: what does true emptiness even mean in an expanding universe? So that's the foundational view. The void as a quiet, dark, simple place. But that quiet nature is deceptive. The greatest surprises are often hidden in the places you least expect to look. A void isn't a perfect vacuum. If you point a telescope into the center of one, past all the stars in the foreground from our own galaxy, and you take a long exposure, a faint light eventually shows up. It's not blackness. You're seeing a few isolated galaxies just drifting in this huge dark space. That's the first clue, the fundamental one, to an order hidden in the void. These aren't the bright, crowded galaxies you find in the filaments of the cosmic web. They're something else. They're the void's own inhabitants, and they hold secrets about the past of the universe. The galaxies that live in these vast deserts, they're often small. They're pristine. They're remarkably unevolved. Astronomers call them dwarf galaxies. They're like living fossils. In the crowded clusters, galaxies are constantly jostled. Their gas gets stripped away. They're transformed by violent encounters. But void galaxies live in profound isolation. They're left alone. They evolve at their own, much slower pace. Surveys like the Void Galaxy Survey show their gas-rich nurseries. They often glow with that blue light of vigorous new star formation. They're less processed. They have lower metallicity, which means fewer heavy elements, the ones forged in earlier generations of stars. In the dense, violent cities of galaxy clusters, these pristine conditions were erased billions of years ago. But here, in the quiet countryside, they persist. There's a galaxy called MCG plus 01020015. It's earned a nickname, the Loneliest Galaxy. It sits in a void so vast, its nearest galactic neighbor is over 1 million light-years away. For context, that's a much greater distance than what lies between our Milky Way and Andromeda. It's a solitary island, an island of stars and gas in an ocean of nothing. So what does its lonely existence tell us? It shows that galactic birth can happen even in the emptiest places, and its slow, undisturbed life offers a clearer window. A window into the conditions of the early universe from before the cosmic web fully formed. These galaxies aren't failed, they aren't stunted, they're just different. They preserve a state that's been lost almost everywhere else. So the void isn't barren, it's a sanctuary, a place where the universe's earliest, most fragile structures could survive. Untouched by the chaos of crowding, this presence of unique life, it challenges our whole concept of what emptiness means. If such delicate fossils can exist there, what other forms of order might be waiting? Even subtler forms, the galaxies are just the beginning. They're the most obvious signposts in a landscape we're only starting to map. The true structure of a void is something you can't see. To find the real order, you have to look past the light. You have to look at the gravity that brings you to dark matter. It's the hidden scaffold, it holds everything together. This unseen mass outweighs all the stars and galaxies we can see, by about 5 to 1. And this mysterious substance, it doesn't just fill the bright clusters. It's in everything. It permeates the vast, dark voids too. That's the invisible skeleton. The cosmic voids have this subtle framework of dark matter. A tenuous web. It traces the large-scale structure even in these empty places. Think of it like a foggy valley. The visible galaxies are just a few scattered lights. But the dark matter is the entire shape of the valley. The hills, the slopes, the gentle bowl. It's there, defining the landscape, even when the lights are few and far between. You can see this in the big computer simulations. The Millennium Run. They show dark matter halos do exist inside voids. They're just lower in mass, quieter. More isolated than the huge halos in galaxy clusters. The dark matter distribution is smoother in a void, but it still forms a connected network, a faint, ghostly echo of the cosmic web. And this invisible skeleton isn't passive. It has a profound influence. It governs the motion of the few visible galaxies in the void. The way those lonely galaxies drift, that subtle tug they feel, it's all from the gravity of this unseen scaffold. Their paths aren't random. They're flowing along the gentle contours of an invisible landscape. That's why studying void dynamics is so important. It's a clean laboratory. By watching how galaxies move in these quiet places, free from the chaos of clusters, scientists can put the strictest constraints on dark matter itself. Is it cold? Is it warm? The serene motion within voids helps answer that. It also gives clues about dark energy, the force accelerating the universe's expansion. The growth, or the suppression of growth, of these vast underdense regions over time is a direct record. A tug of war between gravity and dark energy. Mapping this invisible skeleton is a great challenge. One method is to look for its fingerprints on light. Gravitational lensing, but in its most subtle form. In dense clusters, dark matter bends light into dramatic arcs. In a void, the effect is far weaker. A barely perceptible stretching of background galaxy shapes. It's like trying to detect the slope of a valley by watching a distant mirage shimmer. But by stacking data from many voids, astronomers are starting to chart this faint mass distribution. They're drawing the outlines of the void's true shape, defined not by light but by gravity, so the perspective shifts. A cosmic void isn't defined by an absence of stuff. It's defined by a different arrangement of stuff, a smoother, quieter arrangement of dark matter. An invisible scaffold brings order by providing the underlying shape. The shape everything else must follow. The galaxies are just the visible markers, lanterns hung on a framework we cannot see. This revelation of dark infrastructure, this hidden architecture within the great nothing, it prepares us for the most surprising evidence. A whisper from the dawn of time, imprinted on the void itself, the cosmic microwave background. That invisible structure, it leaves a mark on the oldest light we can see. The cosmic microwave background, that's the afterglow from the Big Bang, released when the universe was just this hot. dense plasma, cooling down into transparent space. This faint glow is everywhere, and when scientists mapped its tiny temperature differences, they saw a pattern. Slightly warmer spots, slightly cooler spots. These are the seeds, the primordial density fluctuations that gravity would later pull into the cosmic web we see now. But some of those spots, they're especially large and cold. And a few of them, astronomers think, might not be primordial at all. They might be a ghostly imprint. An imprint left by the vast cosmic voids that sit between that ancient light and us. That's the integrated Sachs-Wolfe effect. It's subtle, but it's profound. To see it, picture a photon, a particle of light from the CMB. It's been traveling for over 13 billion years to reach us. For most of that trip, it moves through a universe where the large-scale structure is mostly set. But in the last few billion years, dark energy took over. The expansion of the universe started to accelerate. Now, imagine that photon's final approach to Earth. Its path goes right through one of those immense cosmic voids. A region of underdense space that's expanding because of dark energy, a little faster than the universe as a whole. As the photon enters this growing desert, it has to climb out of a gravitational well. But because the void itself is getting bigger and shallower while the photon crosses it, the well isn't as deep when the photon leaves as it was when it entered. The photon loses a tiny bit of energy fighting that changing gravity. And for a photon, losing energy means its light shifts to a longer wavelength. It becomes slightly cooler. When we measure it, that patch of the CMB sky looks like a cold spot. It's not a flaw in the ancient light. It's a signature of the photon's journey through one of the emptiest places in the modern universe. Data from the Planck satellite showed a correlation. Some of the largest cold spots in the CMB map align, just a little too perfectly, with the positions of known supervoids. It's like the oldest photograph of the universe has been retouched by time itself. The most famous example is the CMB cold spot in Eridanus, a region much colder than the surrounding microwave background. For years, it was a major puzzle. Some people proposed exotic explanations, but one leading theory is that it's caused by a supervoid, an immense cosmic desert, maybe a billion light-years across, sitting right in the line of sight. If a void like that exists, the integrated Sachs-Wolfe effect could explain the temperature dip. The search for this void has been intense. Some surveys found evidence of a large underdense region in that direction. Others didn't. The debate continues. Is it a real detection of the effect or a compelling coincidence? This uncertainty is the frontier of cosmology. But the possibility is something else. It means the emptiest places in today's universe are actively writing their names onto the first light of creation. The cosmic microwave background isn't just a snapshot of the infant cosmos anymore. It's also a palimpsest, a document where the later, gentler history of the expanding voids has been inscribed. That connection changes things. Voids aren't passive backdrops. They're dynamic. Their growth, driven by dark energy, has a measurable effect on reality, leaving a faint chill on the light from the dawn of time. If the oldest light carries the fingerprint of the emptiest spaces, you wonder what other subtle forces might be at work in those great expanses. The cold spot in the cosmic background, radiation. It's a kind of signature. Voids aren't empty, they aren't still, they're dynamic. They're engines and they expand at their own pace. That's void swelling. You have the universe's average expansion, the Hubble flow. It's like a steady current. Inside these large voids, that current runs faster. Their internal gravity is weak. There's so little mass pulling inward, not much to hold them back, so they respond more to dark energy's push. They don't just expand with the universe. They outpace it, and that has an effect on the galaxies near a void's edge. Studies of peculiar velocities, the motions of galaxies relative to the Hubble flow. They show these galaxies being pushed outward, carried along on the swelling boundary of the void. Over time, this process sculpts shells, distinct layers around these great nothings. Where galaxies are shepherded by the void's growing influence, It's a large-scale flow, a slow rearrangement of everything, driven by absence. This behavior makes voids a tool. A powerful one for testing the fundamental forces. Measuring their swelling rate gives a direct probe of dark energy's strength. In the quiet of a void, free from the complex gravity of clusters. Any deviation from general relativity would stand out. It's a natural laboratory for gravity itself. Computer simulations show this. They show voids evolving over billions of years. Not as static holes, but as growing, merging entities. They behave like bubbles in a cosmic foam. Their walls thin as they expand. Sometimes they meet. They combine into larger underdense regions, and watching that raises a question. Could our own Milky Way be inside a void? It's a thought experiment. If we are in a local underdensity, even a modest one, it would affect our measurements of the universe's expansion rate. Our local perspective would be skewed. Like trying to gauge a river's speed from an eddy. Some astronomers are investigating this, searching for evidence of a local void. That might explain tensions in the data. To see voids as these accelerating regions reframes them. They aren't passive backgrounds, they're active participants. Their growth reshapes the cosmic web from the inside out. This dynamic nature is in their forms. They aren't perfect spheres. They're complex, ever-changing shapes that tell the story of their own violent birth. And their growth. We imagine a void as a perfect dark sphere, a bubble, but that's not what they are. They are irregular, elongated. Sometimes they look like cosmic sausages. Or these complex, amoeba-like shapes. Their form is an imprint, a direct imprint of the forces that shaped them. To see why, you have to picture the cosmic web as a landscape. A three-dimensional terrain. Mountains and valleys carved by gravity. In that view, a void is a watershed basin. It's the catchment area, where if you dropped a ball, it would roll toward the center of emptiness. That's actually how modern galaxy surveys map them. Surveys like the Sloan. They trace the contours of this density terrain. The boundary of a void isn't a clean edge. It's a wrinkled surface. A dented surface where the underdense region meets the surrounding walls. And those walls are under tension. They're being pulled by the dense clusters at the intersections. That creates tidal forces, a stretching and squeezing effect. It molds the void from the outside. Think of a soft lump of clay in a net. As the net is pulled from all directions, the clay deforms. It flattens, it elongates. That's what happens to a void. The gravitational pull from the filaments and clusters tugs at its boundaries. It keeps it from relaxing into a sphere. There's a famous example, the Gemini void. It's known for its elongated, sausage-like form. Its shape tells a story of the specific massive structures around it. Pulling it into that stretched configuration over billions of years. So every dent in a void's boundary is a fossil record. A record of the tidal forces acting on it since the universe was young. This makes the distribution of void shapes a test. A cosmological test. The statistics of how many are round, how many are elliptical, how many are irregular. That pattern depends on the initial conditions. The tiny quantum fluctuations from the Big Bang, stretched to cosmic size during inflation. Those fluctuations set the pattern for everything. By measuring void shapes today, cosmologists can work backwards. They can test which models of those primordial seeds match the voids we see. It's like finding unique footprints and deducing the anatomy of the creature that made them. The irregularity of void forms adds a layer of complexity to their ordered structure. It shows the order within a void isn't just about what's inside. It's about its relationship to everything outside. Its shape is a dialogue, a conversation between absence and presence, between the empty interior and the crowded cosmic web that surrounds it. That interconnectedness hints at a deeper principle, one that governs not just individual voids but the entire hierarchy of emptiness. That irregular shape is just the beginning. You zoom into one of these great cosmic deserts, and the emptiness itself starts to resolve. It reveals a hidden geography. The void isn't a uniform, featureless plane. It has its own intricate landscape. Inside a vast void, astronomers find smaller subvoids, diminutive bubbles of even lower density, and connecting them like faint threads are tenuous filaments of galaxies. This is the hierarchy of nothingness, a cosmic Russian doll where smaller absences nest inside larger ones. The structure of the void mirrors, in reverse, the fractal nature of the cosmic web. Where the web has dense clusters within filaments within superclusters, the void has subvoids within supervoids. It's a pattern of emptiness that repeats across scales. This self-similarity isn't an accident. It's a direct imprint of the universe's initial conditions, stretched and woven by gravity over billions of years. To see it, scientists use sophisticated multiscale void-finding algorithms. These aren't simple searches for empty circles. They are mathematical tools that can peel back the layers. They identify underdense regions at different size scales, from immense supervoids spanning hundreds of millions of light-years down to much smaller pockets. The algorithms show a cosmos where emptiness has a rich, textured architecture. This hierarchy forms from the bottom up. In the early universe, tiny quantum fluctuations created a spectrum of underdensities. Small regions where matter was slightly less crowded. As gravity worked over eons, these small underdensities began to expand. They merged with their neighbors. They grew into the larger voids we see, but the process isn't perfect. It doesn't erase all trace of the smaller beginnings. The merger history is frozen into the void's structure. You can think of it like raindrops on a window pane. Small droplets form, then flow together into larger streams and pools. But within the large pool, you can still see the faint outlines, the ripples, marking where the original smaller droplets came together. That's the nested structure inside a cosmic void. To quantify this, cosmologists use a statistical tool called the void size function. It's essentially a cosmic census. It counts how many voids of each size exist. The shape of this function, the distribution from the largest supervoids to the smallest minavoids, is a powerful test. It has to match predictions from our models of dark matter, dark energy, and the primordial seeds from inflation. If the hierarchy we observe fits the predictions, it confirms our understanding of cosmic evolution. If it doesn't, it points to something new, something missing from our equations. A real-world example of this nested emptiness is the Sculptor Void Complex. It's a famous underdense region in our cosmic neighborhood. Observations suggest it isn't one simple, smooth void. Instead, it appears to be a complex of several smaller voids, loosely connected, sitting within a larger underdense envelope. It's a clear, observable case of the hierarchical principle, which leads to a question: is there a fundamental limit to how small or how empty a void can be? Could there be, at some tiny scale, a quantum void? A pocket of spacetime where the very concept of density breaks down? While that remains speculation, the observable hierarchy pushes down to scales of a few million light-years. These microvoids, with just a handful of galaxies, are the direct descendants of the faintest underdensities in the infant universe. This changes everything. The order within the cosmic void isn't a single, simple pattern. It's a pattern within a pattern within a pattern. A recursive mystery of absence. Each layer of this hierarchical emptiness is a page in a history book. A book that tells the story of gravity's slow work and the quantum whispers from which all structure grew. To read that story fully, we have to trace these voids back to their absolute origin, to the moment of their conception in the fiery dawn of time. The nested emptiness we see now, that whole structure, it was set from the very start. The origin of cosmic voids isn't in the darkness of space. It's in a flash of light, of energy. To find where they began, you have to go back to the universe's first sliver of a second, to a place ruled by quantum physics. Back then, everything was unimaginably dense and hot. The cosmos was a seething quantum foam. Empty space wasn't still, it was alive with fluctuations. Tiny, temporary bubbles of energy would pop into existence and then vanish. These quantum jitters created minute differences, tiny ripples in the density of matter and energy. Some spots were ever so slightly denser. Others were ever so slightly more sparse. On their own, these differences were subatomic, insignificant, but then inflation happened. A period of faster-than-light expansion in that first fraction of a second. That epoch stretched those quantum ripples. It took those microscopic density differences and blew them up to the size of superclusters and supervoids. The slightly underdense regions, the quantum seeds of emptiness, were inflated into vast regions of lower density. They became the primordial blueprints for the voids. That's the connection experts like Alan Guth and Andre Linde described. The theory of inflation provides the missing link. It explains how the perfectly smooth early universe, the one we see in the cosmic microwave background, could have given birth to the lumpy cosmic web we see today. Those tiny temperature variations in the CMB, the warm and cold spots, are the direct, stretched-out imprints of those same quantum fluctuations. And the statistical pattern of those spots, their size distribution and correlation, is mathematically linked to the pattern of voids we observe billions of years later. The journey from quantum seed to cosmic desert is a story of gravitational evolution. After inflation, the universe was filled with this faint pattern. Over densities and under densities, gravity began its slow work. It's an attractive force, so it pulls matter toward the denser regions, but this has a dual effect. As matter flows into the future filaments and clusters, it drains away from the underdense regions. The slightly emptier patches expand a little faster than the cosmic average, because there's less gravity holding them back. Over billions of years, this process runs away with itself. The underdense regions become emptier and emptier, growing into the vast voids, while the dense regions become the bright web. That's why the spectrum of void sizes we see today, from the smallest minavoids to the largest supervoids, isn't random. It's a fossil record. It encodes precise information about the physics of inflation itself. The relative numbers of large and small voids tell cosmologists about the energy scale of that primordial expansion, and about the nature of the quantum field that drove it. To visualize this, scientists run massive computer simulations. They start with a Gaussian random field, a mathematical representation of those initial quantum fluctuations after inflation. They feed in the laws of physics, dark matter, dark energy, and gravity. Then they let the simulation run for 13.8 billion years of cosmic evolution. And what emerges is a virtual universe that looks uncannily like our own, complete with a cosmic web and a hierarchy of voids that match our observations. It's a stunning validation. The smallest conceivable jitters in the fabric of reality, amplified by inflation and sculpted by gravity, became the largest structures in existence. It makes you think, what does it mean that the grand architecture of emptiness, spanning hundreds of millions of light years, was determined by events so brief and so tiny we have no direct vocabulary for them? This understanding completes the story of void formation. We've traced them from their quantum origins through the dynamic age of the cosmos, to the intricate, nested structures we map today. But this journey leaves one final question. If voids are these great expanding regions, defined by an absence of luminous matter, what truly fills the space inside them? That question about the voids, what's actually in them, it changes what emptiness means. A cosmic void isn't a perfect vacuum. It's filled with this invisible sea. A tenuous, hot plasma. The warm, hot intergalactic medium, the WIM. It's a relic, leftover material from when the cosmic web formed, and it holds a staggering secret. A lot of the universe's normal matter, the baryonic matter that makes up stars and planets and us, it's not in galaxies. It's out here, floating in this million-degree fog inside the great voids. For decades, there was the missing baryon problem. Adding up all the normal matter we could see in stars, galaxies, cold gas, it only came to about half of what the Big Bang said should be there. The WIM is where the rest has been hiding. This gas is incredibly hard to detect, too hot to emit visible light, too diffuse to glow brightly in X-rays on its own. To find it, astronomers use a trick. They point telescopes like Chandra and Hubble at brilliant, distant quasars. As that quasar light travels billions of light-years to us, it passes through these vast intergalactic spaces. The hot gas in the WIM absorbs specific wavelengths of that light, leaves faint fingerprints in the quasar's spectrum. The telltale sign is absorption lines of highly ionized oxygen. Oxygen atoms stripped of most of their electrons by the intense heat. When you see those lines, you're mapping the invisible, tracing the tenuous filaments of this hot gas that weave through the cosmic voids. A ghostly web within the web. How did it get so hot? The story is cosmic violence, now frozen in a diffuse state. As large-scale structure formed, matter flowing into dense filaments and clusters created colossal shock waves. These shocks, traveling millions of miles per hour, heated the intergalactic gas to hundreds of thousands, even millions of degrees. And then feedback from galaxies themselves, powerful winds from supernova, active black holes, pumped energy back out, helped heat and distribute this material into the voids. So the content of nothing is a sparse, seething plasma, a silent ocean of particles that holds the majority of the universe's normal atoms. It's a complete inversion. The brightest, most crowded places, the galaxies, they're actually the minority of normal matter. The true reservoir, the main body of atomic stuff, it's in the dark, hot expanses we once thought were empty. It makes you ask, if this unseen sea fills the voids, what other invisible forces might be at work in there? Could there be subtler structures, woven not from matter, but from something even more elusive, threading through that million-degree fog? That ocean of hot gas might not be the only thing out there in the voids. There's another possibility, a force we usually think about with stars and galaxies. Could these huge, empty places have magnetic fields? It seems contradictory. Magnetic fields come from moving charges, from dynamos in dense plasma. What's moving out there in nothing? But recent radio astronomy studies suggest something. Even in the low density of cosmic voids, there could be large-scale magnetic fields, incredibly weak ones. Ghosts of magnetism stretching for millions of light-years. To find something that faint, astronomers use an effect called Faraday rotation. A radio wave, polarized light, comes from a distant quasar. If it passes through a region with a magnetic field and some free electrons like that sparse plasma, something happens. The field twists the wave's polarization angle. It's a tiny rotation. By measuring how much the polarization from many distant sources is twisted, and mapping how that changes across the sky, scientists can reconstruct the invisible magnetic fields. It's like figuring out the shape of a lens by how it distorts a grid of streetlights. The signals are incredibly subtle. Void magnetic fields would be billions of times weaker than Earth's. Detecting them is like hearing a whisper in a hurricane. But projects like the LAFAR telescope array are built for this. They collect faint radio signals with great sensitivity, looking for those Faraday rotation patterns. Patterns that could only come from vast, diffuse magnetic structures in the cosmic web, even in the empty parts. Where could this magnetism come from? One theory points to the universe's infancy. These could be primordial magnetic fields, generated in the extreme conditions of the Big Bang or during inflation. If that's true, they'd have been stretched and diluted by cosmic expansion, becoming the faint, all-pervading background we might detect today, a fossil from the first moments. Another possibility is the first galaxies and supernova. Powerful outflows from those early, violent objects could have pumped magnetic energy into intergalactic space. Then it was stretched and woven into the expanding voids by the large-scale flows of the cosmic web. The search isn't just for Faraday rotation. Astronomers also look for a faint glow called synchrotron emission. That's the radio light given off when fast electrons spiral along magnetic field lines. Finding a faint, patchy radio haze that lines up with the locations of known voids, with no bright galaxies to explain it, would be a direct signpost. It would mean electrons are being accelerated out there somehow, and a magnetic field is there to make them shine. That detection is still elusive, but it's the next frontier for mapping the void's anatomy. Why does it matter? If confirmed, void magnetic fields would change our understanding of cosmic evolution. They'd provide a new source of pressure, however slight, affecting the sparse gas dynamics in voids. More dramatically, they'd act as highways and barriers for cosmic rays. Those ultra-high-energy particles streaking across the universe. Their paths could be guided by these ghostly magnetic filaments. Tracing the hidden structure of the abyss as they travel, it makes you think, how can a force tied to the chaos of dense, energetic objects persist in the quietest places? The potential for magnetic order in the void adds a new layer to its hidden structure. It suggests that even in the greatest absences, the universe holds a memory of its most energetic beginnings. This search for the faintest whispers of magnetism leads to considering the most dominant energy shaping these voids. An energy that doesn't just fill the emptiness, but actively creates it. That search for the faintest magnetic whispers, it leads to the dominant force shaping these voids. Dark energy. The emptiest places in the cosmos are turning into our most powerful detectors for it. Because the growth of cosmic voids, their evolution, it's exquisitely sensitive to dark energy's properties. This is the force driving the universe's accelerated expansion. And it leaves its clearest fingerprint where there's the least gravity to fight back. In the crowded knots of the cosmic web, the dense regions, the fierce pull of gravity from thousands of galaxies dominates everything. It's chaotic, but in a void, gravity is weak. The inward tug from its sparse matter is feeble. That makes the void's expansion especially responsive to the outward push of dark energy. A void doesn't just expand with the universe's average flow. It swells, it accelerates. Its boundaries move outward faster than the cosmic average. The rate of this swelling, the abundance of voids of different sizes, even their distorted shapes, all of it changes depending on the strength of dark energy. What it is, think of a void as a balloon in a room where the air pressure is slowly increasing. The way the balloon inflates, how quickly its surface stretches, that tells you exactly what the pressure is. Voids are the universe's pressure gauges. To read them, cosmologists use next-generation sky surveys. Missions like the European Space Agency's Euclid telescope. The Vera C. Rubin Observatory's Legacy Survey of Space and Time. These projects aren't just making bigger maps of galaxies. They're engineering precision tools to measure the cosmic void population in unprecedented detail. They will catalog millions of galaxies, trace the cosmic web in 3 dimensions, identify hundreds of thousands of voids across vast cosmic distances. The plan is to compare the statistics of these voids from the observations with predictions from different cosmological models. Each model makes a specific forecast. If dark energy is a simple cosmological constant, like in Einstein's original conception, a fixed strength over time, that model predicts a certain distribution of void sizes and shapes as the universe ages. But if dark energy is something more dynamic, if its strength has changed over billions of years, the void statistics will tell a different story. An example is the void size function. That's the cosmic census counting how many large, medium, and small voids exist. By measuring this function at different epochs, looking at nearby voids and voids billions of light years away, which means looking back in time, scientists can see if it has changed. If they detect a shift in the abundance of giant voids over cosmic history, it could be the smoking gun. Evidence that dark energy is not a constant, but an evolving force. That would be a monumental discovery. It would mean the fate of the universe is governed by something more complex, more strange than we currently imagine. The question becomes profound. Could the answer to the universe's ultimate fate, whether it expands forever into cold darkness or meets some other end, lie in studying its emptiest regions? This puts voids squarely at the forefront of modern cosmology. They are no longer just interesting curiosities or backdrops. They are active, dynamic probes. Clean laboratories where the signal of dark energy is least contaminated by the noise of gravity. But the influence of this mysterious energy, as measured through voids, it may extend right to our own cosmic neighborhood. The possibility touches on a growing tension in our measurements of the universe's present-day expansion rate. The idea of a local void isn't just some distant theory. It might be where we actually live. There's evidence now that our Milky Way isn't in an average part of the universe. We could be in a quiet spot, a kind of suburban area inside a huge cosmic void. Astronomers call it the local void. It's not completely empty, but it's an underdensity. There are fewer galaxies here than the cosmic average. And if that's true, this quiet location could be throwing off our most basic measurements of the cosmos. It could explain one of the biggest puzzles, the Hubble tension. That's the gap between two ways of measuring how fast the universe is expanding right now. One method uses the ancient light from the early universe, the cosmic microwave background, and extrapolates to today. The other method measures it directly by watching nearby galaxies move away. These two methods should agree, but they don't. The local measurements keep showing a faster rate. So what if the local measurement is wrong, not from a math error, but because our perspective is biased? That's the local void idea. If we're inside an underdense region, the gravity around us is unusual. There's less mass pulling on us from the void's center. But the dense walls around us, like the Virgo cluster, pull harder. This imbalance creates a flow, a drift of galaxies, including ours, away from the void and toward the dense regions. That motion adds an extra piece to the recession velocity we measure for nearby galaxies. Their light is redshifted not just by the universe's true expansion, but also by this local gravitational flow. When astronomers calculate the Hubble constant from these motions, they might be including this local drift. It makes expansion look faster here than it really is for the whole universe. It's like measuring the current of a wide river while you're stuck in a fast eddy near the shore. Your measurement of the river's speed will be off. Maps of peculiar velocities show this. They show a coherent stream of galaxies, our local sheet, moving in one direction. Part of that is the pull of our home supercluster, Laniakea. But a big part aligns with pushing away from the local void. This void is immense, maybe 150 million light-years across. We're not at the dead center. We seem to be on its edge, like a town on the border of a great desert. It's a humbling thought. We went from Earth as the center to the Sun, to our galaxy as one of billions. Now we see our place in the large-scale structure might not be special. It might be provincial. We may not live in a bustling cluster, but in a quiet, underpopulated hinterland. That connection makes the void real. It's our cosmic environment. It makes understanding these great nothings urgent. If our location inside a void is distorting our view, how do we see the true, large-scale cosmos? The answer is in the same tools that found the void, pushing our maps into 3 dimensions to see not just where the lights are, but the shape of the darkness between them. Finding the shape of nothing starts with mapping everything. You need a 3-dimensional census of the cosmos. Projects like the Sloan Digital Sky Survey, they've spent decades pointing telescopes at the sky. They're not just taking pictures. They're capturing the spectra of millions of galaxies. That spectral fingerprint gives you a redshift, which is a measure of how much the light has been stretched by the expansion of the universe. And redshift gives you distance, so you plot those millions of positions in 3 dimensions, and you don't have a star chart anymore. You have this pointillist sculpture of the local universe. Spanning billions of light-years, you see the bright knots, the filaments, and you see the huge, gaping holes between them. But to identify a void formally, to define its precise boundary, that's where you need sophisticated algorithms. You can't just draw a circle around an empty spot. Emptiness is relative, the edges are fuzzy. Cosmologists use techniques with names like the watershed algorithm, or Zobov, which stands for Z1s bordering on voidness. These are mathematical tools designed to find the basins in the cosmic terrain. They start with all those galaxy positions. They construct a continuous density field. You take all those individual points and smooth them out into a rolling landscape, hills and valleys. The highest hills are the superclusters. The deepest valleys are the voids. The algorithm's job is to find the bottom of each valley, and then trace the ridge lines that separate one valley from the next. Those ridge lines become the void's boundary. It's like how hydrologists map watersheds on Earth, finding the dividing lines between river basins, but the cosmic map has its own challenges. How do you handle sparse, isolated galaxies that sit far out in the void? Are they part of the void, or do they define a tiny, separate subvoid? How low does the density have to be to count as a void's interior? Different algorithms make different choices. Cosmologists like Nico Hammaus, who helped develop the Zobov method, they spend years refining these definitions. They test their tools not on the real universe, but on simulated ones. Massive computer universes, born from our best theories of dark matter and dark energy, where every galaxy's position is known perfectly. They run their void finders on these mock catalogs. They see how well the identified voids match the true underdense regions in the simulation. This calibration is crucial. It tells them how their tools might be biased, what sizes of voids they might be missing, how to translate a catalog of mathematical voids into a physical understanding of the cosmos. The result of this work is a public resource, like the Sloan Digital Sky Survey Void Catalog. It contains precise data on thousands of cosmic voids, their central coordinates, their effective radii, the densities of galaxies within them, and the densities of the walls that surround them. Each entry is a mathematical portrait of an immense nothing. So when we talk about the Boötes void or the local void, we're not just pointing at a blank spot on a map. We're referring to a rigorously defined volume of space, quantified by its relationship to the luminous matter around it. This raises a subtle point. Our understanding of these cosmic structures is inseparable from the tools we use to define them. The void as a scientific object is shaped by the algorithms that find it. Change the parameters and the map of emptiness changes. That doesn't mean voids aren't real. It means that to study the universe's largest structures, we have to acknowledge how our own methods of seeing influence what we find. The science of mapping nothing is a work of inference. It's the human mind, armed with mathematics and immense datasets, learning to perceive the grand architecture of absence by carefully charting the presence of light. And with these precise maps, we can ask a new kind of historical question, not just what voids are, but how they have changed. Can we look back in time and watch the great cosmic deserts as they were forming? Those maps give us a timeline. We can watch voids grow. Looking into deep space is looking back in time. Light from a galaxy 10 billion light-years away shows us the universe as it was 10 billion years ago. So by cataloging voids at different distances, you trace their life story. From the cosmic dawn to now, it's like a photo album. Each page is a different era. The earliest pages, when the universe was just a few billion years old, show a different picture. The cosmic web was still knitting itself together. In those deep surveys, like Hubble's frontier fields, they don't see the vast, clean deserts. They see proto-voids, the seeds of future emptiness. They were smaller then, and denser relatively. They weren't the starkly empty regions we know. They were underdense patches in a universe that was much denser overall. Think of a sponge that hasn't fully expanded. The holes are there, but they are tighter, more packed together, filled with more material. These early voids were also far more numerous. The universe was a foam of countless small bubbles. Then gravity did its work. Over billions of years, it pulled matter out of these underdense regions into the growing filaments and clusters. As matter drained away, the voids began to expand. Their boundaries pushed outward, and like soap bubbles, neighboring voids began to touch and merge. Two smaller voids would share a thin wall of galaxies. That wall would stretch, grow tenuous, finally rupture. The two voids would become one larger, more irregular void. This merging and accretion is how the giant supervoids of today were built. A long history of cosmic consolidation. The galaxies inside these voids tell their own story. In the early universe, void galaxies were more common, more active. With more gas available, many were vigorous star-forming dwarfs, glowing blue with newborn stars. As the void expanded and the gas was consumed or pushed away, that activity slowed. Some galaxies simply used up their fuel. Others were quenched by the gentle, relentless heating of the intergalactic medium. So today, the void galaxies we see are often quieter, more isolated fossils. Cosmologists run side-by-side simulations to visualize this. One frame shows a slice of the universe from 10 billion years ago. A busy, fine-grained tapestry, small filaments and many small, packed voids. The next frame shows the present day. The web is coarser, the filaments are thicker, more defined. And the voids are fewer, but each one is immense, having swallowed its neighbors to become a dominant feature. This raises a question about the far future. What happens to voids as dark energy accelerates the expansion? In the coming tens of billions of years, the swelling intensifies. Voids will grow so vast their walls thin to almost nothing. The faint threads of the cosmic web will stretch and snap. Galaxies on the void boundaries will be swept away, pulled into the remaining dense knots or left isolated in the growing darkness. The universe becomes a place of isolated island universes, separated by ever-widening gulfs of true emptiness. The great deserts become the entire landscape. Watching voids through time is more than studying structure. It's watching the biography of the cosmos, written in the slow growth of absence. And if their past is a story of merging and expansion, their ultimate future may be one of complete and silent dominion. That final page in the album, it's just the void. Trillions of years out, that's what's left. The accelerated expansion, it doesn't just keep going, it wins. And the voids we see now, those isolated places, they do something. They merge. The boundaries of neighboring supervoids, they meet. Their walls of galaxies, they thin out to nothing. And they coalesce into one mega void. A single desert that fills almost the entire observable universe. Inside that emptiness, whatever's left is completely isolated. First, the last galaxy clusters get torn apart. The space between their galaxies expands faster than gravity can pull them together. Then you're left with individual galaxies. These lonely island universes, and finally, even the galaxies might come apart, leaving only the most tightly bound things, orphaned stars, black holes. Drifting in an expanse that's just cooling and darkening. That's the predicted end state. From the models of eternal inflation, the heat death. A cosmos where all the useful energy gradients, the ones that drive stars and life and thought, they've been smoothed away. Into a uniform, cold stillness. This process has a name, void dominance. It's the phase where the expanding voids, they aren't just between the cosmic web anymore. They become the web. They are the entire fabric. The bright knots of the web, the last structures, they aren't destroyed by an explosion. It's a relentless, gentle stretching. They're pulled apart by the geometry of space itself, which is being generated at an ever-increasing rate, inside the voids that surround them, and that leads to an implication. A profound one. In that future, the very idea of cosmology, studying the universe as a whole, it becomes impossible. For any observers surviving in one of those last island galaxies, their observable universe will have shrunk dramatically, because the space between galaxies is expanding faster than light can cross it. No light from any other galaxy will ever reach them again. Their future light cone, the region they can ever get information from, it will contain only their own gravitationally bound group. Everything else recedes beyond an event horizon. Vanishing from their view, from any possibility of detection, it will be, for them, as if their galaxy is the only thing that exists, in an infinite black void. The universe becomes not just dark, but unknowable. New cosmological information stops arriving. The cosmic microwave background redshifts into undetectability. The redshift of distant galaxies approaches infinity. The history of the universe, the evidence of the Big Bang, the large-scale structure we study now, it's erased from the future sky. A universe that has forgotten its own past. So this ultimate fate, written by the voids, it tells us something about our moment now. It underscores with terrible clarity that we live in a privileged era. A narrow window in time, when the universe is transparent enough, structured enough, interconnected enough for us to see its grand architecture, to deduce its history. We can see the voids and the web. We can measure the primordial light. We are building a map of everything at the very time when such a map is still possible to make. Studying the subtle order within voids today, then, is an act of profound urgency. It's not just cataloging empty space. It's decoding the blueprint of the universe's destiny while we still can. These great nothings, they are the architects of the end. And by understanding the rules of their construction, the patterns in their emptiness, we are reading the final chapter of the story. At its very beginning, that final quiet control makes the order we see inside voids now even more striking. One of the first specific puzzles from the data is about the galaxies that live in these deserts. Their spins might not be random. Observations suggest the small dwarf galaxies in voids could have their rotation axes aligned with each other, or even aligned with the large-scale structure of the void walls. Think of spinning tops on a table. If they were placed at random, their axes would point everywhere. But if you came back and found them all spinning with their poles pointing roughly the same way, you'd know something coordinated that setup. That's the hint astronomers are seeing in cosmic voids. This alignment, if it's real, is a direct challenge. The standard model of galaxy formation predicts random orientations. Galaxies get their spin from the chaotic mergers of smaller clumps early on. Their final rotation direction should be as unique as a fingerprint. Finding a pattern, a preferred direction for galaxies scattered across millions of light-years of emptiness, suggests a hidden hand. A hand that worked on a scale far larger than any single galaxy. Studies like the Alpha survey, which maps neutral hydrogen gas, have seen curious things. They looked at hydrogen-rich dwarf galaxies in voids. They measured the orientation of their spinning gas disks from the Doppler shift in radio emissions. The statistical analysis hinted these galaxies might be spinning in a coordinated way. Their axes seemed to show a weak preference, a preference for aligning with the direction of the nearest filament, or with the plane of the void's boundary wall. It's a subtle signal buried in noise, but it persists. What could cause it? Cosmologists look at a few profound possibilities. The first goes back to the very beginning, to tidal torque theory. In the infant universe, as proto-galaxies condensed from the cosmic web, they didn't just collapse. They were stretched and twisted by gravitational tides from neighboring large-scale structures. Imagine a lump of dough being pulled in different directions by surrounding anchors. That pull could impart a spin. And if the tidal forces were coherent over a vast region, like across the gentle slope of a primordial void, it could seed aligned rotations in many emerging galaxies at once. Their spins would be fossilized directions, pointing back to the geometry of the cosmos when they were born. Another possibility involves coherent magnetic fields threading the voids. Those ghostly magnetic filaments, if they are real and strong enough, could act like cosmic guide rails. As gas collapses to form a galaxy, the magnetic field could channel the flow. It could impart a specific angular momentum, forcing the resulting spin to align with the field lines, a universe-wide version of how iron filings align with a magnet. A third idea points to cosmic flows, the gentle, large-scale streaming of matter along the walls of voids and into filaments. This coherent motion could shear and shape the gas that eventually forms void galaxies, spinning them up like leaves caught in a broad, slow river current. Detecting these alignments is a monumental task of statistics. You can't look at two galaxies and declare a pattern. Researchers have to analyze hundreds, even thousands of void galaxies, They measure their position angles carefully. They compare them to the local direction of the cosmic web. They use complex statistical tests to see if the distribution of angles is truly non-random, or if it could just be a fluke of a small sample. The debate is ongoing. Some teams report a significant signal. Others find the data consistent with randomness. The mystery is still open. One example comes from studies of the Lynx Ursa Major Void region. There, a small group of dwarf galaxies on the shell of the large void appeared to show a curious alignment in their rotational axes. They seemed to be spinning in a plane parallel to the local surface of the void. As if the void wall itself had imprinted a preferred direction on these fragile island universes. This leads to a reflective question. How could information, a preferred direction for spin, be communicated across the vast emptiness of a void? To coordinate galaxies that are forever isolated from one another, they don't touch. Their gravity barely influences each other. The answer must lie in the initial conditions. In a blueprint set when the universe was smooth and tiny, a pattern woven into the fabric of space that only manifests billions of years later in the spin of lonely galaxies. This mysterious alignment hints at a deeper level of cosmic organization, something our standard models don't account for. It suggests that emptiness has a grain, a texture that guides the evolution of everything within it. And if the quiet spin of galaxies holds such a secret, what might we hear if we listen to the voids in a different part of the spectrum? A place where silence gives way to an unexpected faint roar. That coordinated spin of galaxies might be the first whisper, but there's a second signal. Something even stranger. It's coming from the great voids, a ghostly light. Radio telescopes are scanning the deepest, quietest parts of the sky, and they're picking up something they shouldn't. Patches of faint, diffuse radio emission with no visible source, no bright galaxy, no active black hole, just a soft, persistent glow of radio waves. Coming from the cosmic deserts themselves, that glow is synchrotron radiation. It's the signature of high-energy electrons. Electrons spiraling at nearly light speed through magnetic fields. Finding it here in the emptiest regions is a profound puzzle. Because to make that light, you need two things. You need relativistic electrons, and you need magnetic fields strong enough to bend their paths. Both of those are products of violent, energetic events. Supernova explosions, galactic collisions, the furious jets from supermassive black holes, all the things that are conspicuously absent in the sparse tranquility of a void. So what's accelerating electrons to such speeds in a place of profound quiet? And where are the magnetic fields coming from to make them shine? That's the mystery of the radio ghosts. Projects like the LAFAR telescope in Europe are built to listen for these faintest cosmic whispers. Its vast array collects long-wavelength radio light with exquisite sensitivity, perfect for mapping large, diffuse structures. And in the data, astronomers have begun to identify these patches. These enigmatic smears of radio emission, and they align. They align just a little too perfectly with the mapped locations of known cosmic voids. They've been given names. Radio relics, radio ghosts, but these void signals are different from the sharp, powerful relics found in crashing galaxy clusters. These are softer, more spread out, like a fading afterglow from an event no one witnessed. So where could this energy come from? Cosmologists are exploring several possibilities. Some are compelling, some are exotic. One leading idea points to the ancient, violent history of the cosmic web itself. Billions of years ago, as the first massive structures were forming, colossal shock waves rippled through the intergalactic medium. These weren't explosions. They were vast, slow-moving walls of pressure, generated as matter flowed into the growing filaments. If such a shock wave passed through a region that would later become a void, it could have left something behind. A population of accelerated electrons, and it could have amplified any primordial magnetic fields. The radio glow we see today would be the dying echo of that ancient violence. A fossilized shock, frozen in time as the void expanded around it. Another possibility involves the void's own growth. As a void swells, its boundaries push outward into the surrounding web. This expansion could generate very faint, continuous accretion shocks at its edges, like the gentle bow wave of a ship moving through still water, but on a cosmic scale. These weak shocks might be just powerful enough to re-accelerate electrons and sustain a faint radio halo. It would mean the void itself is the engine, its growth powering a subtle light show. Then there are the more speculative ideas. Could this be evidence of exotic physics? Some theorists have proposed the glow could come from dark matter, from the decay or annihilation of dark matter particles. If dark matter is not perfectly stable, but can occasionally interact with itself, those rare interactions could produce standard model particles, including electrons and positrons. A void, with its vast volume and lack of competing light sources, might be the ideal place to see it. The faint collective glow of such dark matter decay. It's a long shot, but the unexplained nature of the signal keeps such possibilities on the table. The detective work is incredibly difficult. The foremost challenge is simply proving the emission is truly coming from the void, and not from something in the foreground. Our own Milky Way emits a diffuse radio fog. Distant, unseen galaxy clusters could have faint, extended halos that blur into the signal. Researchers have to use sophisticated statistical techniques to subtract all known foregrounds and backgrounds. They stack data from many similar voids to see if a consistent signal rises above the noise. It's a painstaking process of elimination. One intriguing case study comes from a region in the northern sky. Surveys identified a large, diffuse radio blob, a faint smudge of emission spanning millions of light years. Astronomers cross-referenced this with three-dimensional maps of galaxy positions. They found it sat squarely within a known cosmic void. No bright radio galaxies were inside it. No recent, massive cluster merger was known to have occurred there. It was just a patch of silent radio light, hanging in an immense nothing. This raises a question. What does it mean for the quietest places to be sites of such subtle, high-energy activity? It suggests that even in the greatest absences, the universe retains a memory of violence, or harbors ongoing processes we don't yet understand. The voids are not inert backdrops. They are dynamic, complex environments. Their apparent stillness is an illusion, masking a rich history. A history of gravitational tides, shock waves, and perhaps even the slow decay of the universe's most mysterious substance. This enigmatic glow forces a reconsideration. The void is not a passive emptiness. It's an entity with its own energetic biography. And if the energy within a void can leave such a faint imprint on the radio sky, what other, more subtle signatures might be woven into the shapes of these great cosmic bubbles? There's this faint radio glow. It hints at some hidden energy inside the void, but the shape of the void, that's a different kind of mystery, a geometric one. Out in the cosmic desert, most of the forms are irregular, stretched, but a few of them stand out. They're nearly spherical. In a universe shaped by chaotic gravity, that kind of symmetry is unexpected. How can a region of nothing, growing for billions of years, keep the shape of a perfect bubble? That sphericity is the third puzzle. Most voids get flattened or elongated. That's from the gravitational pull of the filaments and clusters around them. But a distinct subset. They appear almost perfectly round. Cosmological simulations tell us these are rare. When researchers run mock universes, they find the vast majority of voids are deformed. The statistics show a truly spherical void, one that defies the stretching forces, is an outlier. Its existence asks a question of origins. Is it a statistical fluke? A chance arrangement where the outside tidal forces just happen to cancel out? Or is its shape a fossil? Something preserving conditions from the universe's first moments? To answer that, scientists measure sphericity with precision. They don't just look and call it round. They calculate its eigenvalues, mathematical descriptors of its shape. They come from the positions of the galaxies on its boundary. A perfect sphere would have equal eigenvalues in all three dimensions. Most voids show one dimension much shorter or longer than the others, evidence of flattening or stretching. But the rare spherical candidates, their values are nearly identical. This data gets compared against massive mock catalogs from simulations. The question is simple. Do our observed spherical voids appear more often than the standard model predicts? If they do, it suggests our models are missing a piece of physics. One compelling candidate came from the Sloan Digital Sky Survey data. Astronomers identified a void. Effective radius of about 100 million light-years. Its boundary, traced by the sparse galaxies on its edge, formed a shell of remarkable geometric consistency. It stood out from its neighbors, which were twisted into complex, amoeboid shapes. This cosmic perfect bubble appeared suspended in the web, a sphere of quietude amidst the gravitational chaos. Its geometric purity felt alien, as if it belonged to a different set of rules. This leads to a possibility. Could these spherical voids be relics from a time before the cosmic web itself? One exotic theory points to the era of cosmic inflation. If our universe underwent a phase transition as it cooled, like water freezing into ice, bubbles of a new vacuum state could have formed and collided. A spherical void might be the fossilized imprint of one such primordial bubble, a defect in spacetime inflated to cosmic size. Another idea suggests they could be the shadows of pre-inflationary structures, rare regions that were somehow protected from the tidal distortions that shaped everything else. Their roundness would then be a direct snapshot of the universe in its infancy, before gravity began its long work of shearing and sculpting. Alternatively, their shape might come from a uniquely symmetric history. Perhaps this void formed from the near-perfect merger of several smaller voids, their intersecting boundaries smoothed out into a single, round cavity. It would be a cosmic accident of perfect balance, a peaceful agreement between expanding regions of nothingness. Yet even this explanation feels special, because such symmetry is fragile in a universe of competing gravitational pulls. What does it mean to find a perfect geometric form in the cosmos? These spherical voids stand as silent monuments. Their contrast with the tangled web around them is stark. They speak of initial conditions frozen in time, of a moment when the universe was simpler, smoother, perhaps governed by symmetries that have since been broken. To study them is to look for the cleanest fingerprint on a dusty pane of glass. They offer a potential window, not just into the emptiness of space, but into the pristine order from which all complexity later emerged. If their shape is indeed a primordial signature, then each one is a time capsule. A perfectly round capsule, floating in the dark, holding a secret from the first fraction of a second of everything. A perfect sphere of nothing is one ghost. There's another kind, though, far more energetic. The fourth mystery asks if these dark voids could be sources of the universe's most powerful light. Could they be emitting gamma rays? These are photons with immense energy, billions of times more energetic than visible light. They usually come from the most violent places, the crushing environments around neutron stars, the relativistic jets of supermassive black holes, supernova explosions, all the places a void is not. Yet some astrophysicists are looking there, because the source might not be anything we can see. It could be the dark matter itself. The theory is simple. If dark matter is made of particles, and if those particles can interact, they might annihilate on contact. Or a heavier, unstable dark matter particle might decay into lighter ones. Both processes could release energy, and that energy could manifest as a spray of standard model particles, including high-energy gamma-ray photons. Now, where would you look? In a dense galaxy cluster, the dark matter signal would be strong but drowned out, blinded by the gamma-ray glare from all the other astrophysical processes. A cosmic void, by contrast, is almost perfectly dark in gamma rays from conventional sources. It's a clean, quiet room. If dark matter annihilation or decay is happening uniformly throughout the universe, the signal from a void might be the purest one to detect. Its emptiness makes it an ideal trap for a faint, universal glow. Scientists use data from instruments like the Fermi Gamma Ray Space Telescope. Fermi has spent years scanning the entire sky, building a detailed map of the gamma ray universe. The map shows a diffuse, isotropic background, a kind of fog of gamma rays coming from all directions. The challenge is to see if there are any subtle excesses in that fog that line up with the known locations of large cosmic voids. It's like listening for a faint hum in a room full of white noise, and checking if that hum gets slightly louder when you point your ear toward a particular, empty corner. The particle physics behind this is fascinating. The dark matter candidates have names like sterile neutrinos or action-like particles, hypothetical particles that interact so weakly with normal matter they've evaded all direct detection. In certain models, when they annihilate, they could produce gamma rays with a very specific energy signature. A spike in the gamma ray spectrum at that energy, coming from a void, would be a revolutionary discovery. The first indirect detection of dark matter's particle nature. The practical search is a monumental task of data sifting. Researchers take the three-dimensional map of cosmic voids from optical galaxy surveys. They overlay the Fermi gamma ray map. For each void, they calculate the total gamma ray flux from its direction, subtracting the expected foreground from our own galaxy and from other known, distant sources. Then they stack the data from hundreds of voids together, amplifying any potential weak signal that might be common to all of them. It's statistical archaeology. Digging for a consistent whisper buried under cosmic static. One of the most famous targets is the Boötes void. Its immense size and well-mapped boundaries make it a prime candidate. If a certain type of dark matter is clustered even in these underdense regions, the Boötes void, with its sheer volume, could accumulate enough to produce a detectable excess of gamma rays. Several studies have pointed telescopes in its direction, analyzing years of Fermi data. The results so far are inconclusive. There are hints, slight statistical nudges, but nothing definitive enough to claim a discovery. The signal remains elusive, dancing at the very edge of the instrument's sensitivity and our statistical certainty. This potential link is profound. It turns the largest, emptiest structures in the universe into natural detectors for the smallest, most elusive particles. A cosmic void becomes a laboratory for particle physics. The scale is incomprehensible, but the quarry is subatomic. It bridges two extremes, the cosmology of the vast and the physics of the infinitesimal. If a void ever whispers to us in gamma rays, it won't just tell us about the structure of space. It will tell us what the universe is ultimately made of. Looking for gamma rays means looking for something you can't see. But sometimes, to understand a void, you just look straight through it. That's the fifth mystery, the void transparency test. In theory, a cosmic void should be like a perfectly clear window. There's so little stuff in the way. Light from something incredibly bright and far away, like a quasar, should come through almost unchanged. Its trip across hundreds of millions of light-years of near-empty space should be clean. Very little scattering, very little absorption. You could use these huge voids as perfect sightlines. You could see deeper into the cosmos than from anywhere else. But the reality is different. It's puzzling. Scientists point their instruments at quasars. They know the light from these quasars pass through a mapped supervoid, and sometimes they see something unexpected. The quasar's spectrum, that rainbow fingerprint of its light, isn't perfectly smooth. It's marked with dark absorption lines. Those are the signatures of cool gas clouds. Clouds floating in the huge spaces between galaxies. The confusing part isn't that the lines are there. It's that there are often more of them, and in different patterns. More than our best models of void structure predict. The emptiest places in the universe seem to have more in the way than they should. This detective work is for the quasar absorption line astronomers. Their main tool is the Lyman-Alpha forest. It's this beautiful, complex pattern of absorption lines. It happens when a quasar's light passes through clouds of neutral hydrogen gas at different distances along its path. Each cloud, at a specific redshift, absorbs a tiny, specific slice of the quasar's ultraviolet light. The result looks like a tree's roots, a dense tangle of absorption lines. In the crowded parts of the cosmic web, the forest is thick. But when the sightline goes through a known void, astronomers expect the forest to thin out. They expect a clearing, sometimes they see it, but other times the forest stays surprisingly dense, or it shows a peculiar pattern, a pattern that suggests the gas isn't smooth. It's clumped into more discrete clouds than anyone expected. What are these clouds? The leading idea goes back to the warm, hot intergalactic medium, the WIM. Our models say this million-degree plasma should be spread out in a smooth, diffuse way inside a void. But these absorption lines tell a different story. They point to cooler, denser filaments or blobs of gas, embedded within the hot WIM. It's like the ocean of hot plasma has cooler currents and eddies inside it. These could be the shredded remains of small galaxies, galaxies torn apart by tidal forces long ago. Or they could be pristine gas that never fully heated up. Another possibility is that they're the extended halos of faint, unseen dwarf galaxies. Those lonely void galaxies we talked about earlier. They're known to be surrounded by huge cocoons of cool hydrogen gas. Light from a distant quasar might be skimming the edges of dozens of these invisible halos as it crosses the void. Each one leaves its own faint absorption line on the spectrum. Take a specific quasar. Its light has been traveling for over 10 billion years. Astronomers use 3D maps from surveys like Sloan. They trace its path. They see it passes right through the heart of a cataloged supervoid, a region hundreds of millions of light years across, a region with a known, very low density of galaxies. They take an extremely detailed spectrum of that quasar with an instrument like the Keck telescope. The theoretical prediction is a spectrum with a noticeable gap, a region with far fewer absorption lines, corresponding to the distance of the void. But the actual data might show something else. The gap is there. But it's not empty. It's sprinkled with a distinct set of absorption lines. These lines are the ghosts of cool gas clouds. Clouds our maps of luminous matter didn't predict. Floating in the great dark. By analyzing the strength and spacing of these lines, researchers can estimate the density and temperature of this hidden material. They're using the quasar as a cosmic flashlight, and the void as a shadow theater, to see the silhouettes of structures too faint to light up on their own. This unexpected lack of perfect transparency leads to a question. Why would the universe's clearest windows still have a faint film? It challenges a basic assumption. The assumption about how normal matter is distributed in the universe. We thought we understood the hierarchy. Hot, diffuse WIM filling the voids, galaxies and their cool gas halos confined to the web. But these absorption lines suggest the cool gas has leaked far out into the emptiness. It exists in a more complex, clumpy state than our simulations produce. This has big implications, especially for studying the reionization epoch. That was the period in the early universe when the first stars and galaxies lit up. When they burned away the fog of neutral hydrogen that filled all of space. To understand that era, astronomers look for the absorption signatures of the very last patches of that primordial fog. They look in the spectra of the most distant quasars. If even modern-day voids contain unexpected pockets of cooler gas, it means the distribution of material during reionization was likely even more intricate, more patchy than we think. Our clearest windows to that distant time might be slightly fogged by our misunderstanding of the emptiness in front of us. So the void transparency test becomes a vital diagnostic. Every absorption line in a quasar spectrum that passes through a void is a clue to the true, fine-grained structure of the most diffuse matter in the cosmos. It tells us that emptiness is not simple. Even the great deserts have their hidden oases, their subtle weather. and mapping this faint, cool mist within the hot void may be the key. The key to finally accounting for every last atom of the universe's missing normal matter. It turns a simple act of looking into a deep investigation. An investigation of what it means for space to be truly empty. There's a film, a faint texture on the cosmic window, but underneath that, there's a rhythm. A pattern woven into the void itself. That's the sixth mystery, and it starts with a sound, the first sound of the universe. In the beginning, everything was a seething plasma. A dense soup. Gravity tried to pull matter into clumps, but the radiation pressure pushed back. That struggle created oscillations, spherical sound waves ringing through the primordial fluid. Then the universe cooled. Atoms formed. That was around 380,000 years after the Big Bang, and the music stopped. The waves froze in place. They left a permanent imprint on the distribution of matter, a preferred scale, a cosmic ruler etched into the heavens. It's called the Baryon acoustic oscillation. The BOO. That frozen wave created a signature. Matter tended to clump at a specific distance from any initial dense spot. You can picture a stone dropped in a pond. The stone is the dense spot. The ripples spreading out are the sound waves. When they freeze, you're left with the central stone, and then a ring of material at the distance the ripple traveled. For the universe, that distance is colossal. About 150 megaparsecs, nearly 500 million light-years. For decades, astronomers have detected this signal by studying galaxies. They measure distances between millions of galaxies. They find a slight excess of pairs separated by that magic scale. It's a robust measuring stick. But now there's a new frontier. A mystery in the emptiness. Could that same ancient echo be detected not in where the galaxies are, but in where they are not? Could the pattern of the voids themselves carry the memory of that first sound? That's the quest. To measure the void BOO signal. Instead of counting galaxies, cosmologists are mapping the voids between them. They use data from massive surveys, BOSS, EBOSS. These have charted the three-dimensional positions of millions of galaxies. From these maps, they identify thousands of cosmic voids. Then they don't look at the voids in isolation. They study their relationships. They calculate the void correlation function. It's a statistical measure of how voids are distributed relative to each other. If voids were placed randomly, this function would be flat. But if the Baryon acoustic oscillations influenced the early underdensities, the seeds of voids, then voids should also show a preference. A preference to be separated by a specific scale. The scale of that first ripple, and the data is starting to show it. In the statistical plots, amidst the noise, there's a faint bump. A significant bump. At a separation of roughly 150 megaparsecs. It's the echo of the sound wave, seen in the architecture of absence. The physics is elegant. Those early sound waves created alternating shells. Shells of slightly higher and lower density. The low-density shells became the seeds for the vast voids we see today. And because those seeds were laid down on a specific scale, the voids that grew from them retain a ghostly correlation to that scale. The empty centers, the surrounding walls, they're all part of this frozen acoustic pattern. Measuring the BOO scale with voids gives you something powerful. A complementary probe, an independent one. Galaxy-based measurements can be affected by bias. By how galaxies don't perfectly trace the underlying dark matter, but voids. These huge regions defined by a lack of galaxies, they offer a cleaner view. They trace the dark matter distribution more directly. Their correlation signal is less contaminated by the complex physics of galaxy formation. This lets scientists put tighter constraints on fundamental parameters. The amount of dark energy, the curvature of the universe. There's an example from the EBOSS data. Researchers identified a clean sample of voids, calculated their correlation function, applied statistical techniques to isolate the signal. The resulting plot showed a clear peak, a peak at the expected scale. It was a whisper from the dawn of time, heard not in a crowd but in the quiet spaces between the crowds. It's a staggering thought. the emptiest places in the cosmos. Regions expanding and quieting for over 13 billion years. They still hold a perfect imprint. An imprint of a moment when the entire universe was ringing like a bell. This detection turns cosmic voids into something more. Not just deserts, not just laboratories, it turns them into cosmic tuning forks. They vibrate, not with sound we can hear, but with a statistical signature. A scale set in the first moments. By listening to the pattern of their silence, we can tune our understanding. The universe's composition, its expansion. We can tune it with remarkable precision. If the geometry of emptiness can sing the universe's oldest song, what other primordial secrets might be written in the dark? There's this pattern, an echo in the void. It leads to a deeper statistical whisper. It connects the emptiest places now to the very first light. That's the seventh mystery. The void CMB Cross-Correlation. We know the integrated Sachs-Wolfe effect. A void can leave a cold spot on the cosmic microwave background, but that's one way. The void affects the CMB. This new puzzle is a two-way conversation, a subtle statistical link between where voids sit today and specific, large-scale patterns in that ancient baby picture. So cosmologists take the latest void catalogs. They overlay them onto the CMB map from Planck. They perform a statistical dance. They calculate correlation functions. They look for any sign that the positions or shapes of thousands of voids align even slightly with the warm and cold patches in the primordial light. The standard model makes a specific prediction. Dark matter, cosmological constant. It predicts what that correlation should look like. It should be faint. It should follow a particular mathematical curve. But some independent analyses have found hints. The observed correlation appears subtly stronger at certain angular scales. Or it shows a pattern that diverges from the predicted curve. It's not a dramatic discovery. It's a persistent statistical nudge, a slight tension in the data. As if the universe's adult skeleton of voids and its infant photograph are linked by a thread the standard model doesn't account for. So what could this mean? Experts point to several possibilities. One is early dark energy. The idea that dark energy wasn't always constant. Maybe it was active and dynamic in the universe's first few 100,000 years. A brief burst of it would have altered how sound waves propagated in the primordial plasma. That would change the statistical pattern of the CMB, and it would change how the seeds for future voids were planted. The result would be an anomalous cross-correlation, one our standard models can't reproduce. Another possibility points to the very beginning, non-Gaussian initial conditions. Our standard model assumes the quantum fluctuations from inflation were Gaussian. Their distribution followed a specific bell curve randomness. But what if they weren't perfectly Gaussian? What if there were tiny correlations between fluctuations of different scales from the start? That primordial memory would imprint itself both on the CMB patterns and on the eventual distribution of voids. Their modern correlation would carry that fossil imprint, a more complex birth. Then there's the humbling alternative, systematic error. The maps are monuments of human ingenuity, but they're not perfect. Could a tiny, unaccounted for bias in how we identify voids create this? Or a faint foreground contamination in the CMB data? Teams test this. They create thousands of simulated universes based on the standard model. They run their void finders on these perfect mock datasets. They ask, in how many of these simulated runs do we see a correlation as anomalous as the one in our real data? If it's 1 in 20, the tension is interesting. If it's 1 in 1,000, it becomes compelling. There's an illustrative example in the study of specific multipole moments. The CMB map can be broken down into a spectrum of these moments. Each describes patterns at a certain angular size. Some researchers have noted that the power in a particular range of multipoles, a certain size of blotches on the CMB, seems statistically linked to the presence of one of the largest known underdensities in our local universe. It's as if that vast modern void is casting a longer shadow back in time than our physics allows. This enigma sits at the heart of cosmology. It asks if the two most fundamental maps we have, the first light and the final structure, are telling us the same story. Or if, in their quiet statistical dialogue, they are hinting at a richer narrative, one that requires us to rewrite a chapter. Are we hearing a faint signal of physics beyond our current standard model? Or are we listening so intently to the silence of the void that we are hearing the echoes of our own methods? The search is a meticulous process, listening, comparing, questioning. Using the greatest emptiness as a guide to the universe's first moments. That ancient light gives us a statistical whisper, and it leads to a different hunt. A search for the original ingredients, everything. The eighth mystery, it turns these cosmic voids into time capsules. They could hold the last untouched samples. Primordial gas. The first stars to ignite, they were nothing like what came later. Theorists call them population 3 stars, behemoths, hundreds of times the mass of our Sun. They lived fast, they died in colossal explosions, and in their furious hearts they forged the first heavy elements. Carbon, oxygen, silicon, iron. They scattered those seeds into the cosmos. That act, that cosmic pollution, it changed everything. Every star born after that, our Sun included, formed from gas that was already enriched by those first giants. So to understand the true original state, you need gas that never met those first stars. Gas with virtually zero metallicity, no heavy elements. Just hydrogen and helium, as it was after the Big Bang. Where could a relic like that survive for over 13 billion years? The answer points to the cosmic voids. In the dense environments, the clusters and filaments, gas is constantly stirred, mixed, recycled through generations of stars. It's all polluted. But in the profound isolation of a void, a pocket of gas could have just sat there. Undisturbed, a quiet backwater, bypassed by the whole epic cycle, star birth and death, that makes the search for pristine gas in voids a kind of holy grail. Astronomers use ultra-deep spectroscopic surveys, instruments like the Very Large Telescope, the James Webb Space Telescope. They stare into the emptiness. They're not just looking for galaxies, they're looking for the faint, ghostly signatures of the gas itself. The primary tool, again, is the quasar absorption line. By analyzing the precise pattern of lines in a quasar's spectrum, light that passes through a void, scientists can measure the metallicity of the intervening gas clouds. They look for the telltale absence, the absence of lines from oxygen, carbon, silicon. A spectrum showing only the clean lines of hydrogen and helium. That would be a monumental discovery. The challenge is immense. Even a single tiny dwarf galaxy with one brief episode of star formation can pollute its entire local reservoir. The supernova wind from just one small star can spread metals across thousands of light years. So finding a cloud that completely avoided enrichment requires a perfect storm of isolation. A void provides that environment, but it's not a guarantee. Researchers map the sightlines to distant quasars. They ensure the beam travels through the core of a known, massive void, far from any catalogued dwarf galaxies. Then they take spectra of exquisite sensitivity. They search for the faintest absorption features, and more importantly, for the profound lack of them. One of the most promising leads came from a quasar, J0343-2450. Its light passed through an immense void. Analysis of its spectrum revealed a cloud of gas. With a metallicity less than 1/10,000th of the Sun's, it wasn't perfectly pristine, but it was the cleanest gas ever detected. It suggested a region barely touched by stellar processes. A near miss that hints at the possibility of finding the real thing. The parallel hunt is for a living population 3 star. Most theorists believe those first stars were all too massive to survive. But some models suggest smaller versions could have formed. If any still shine, they'd likely be found in the most pristine environments, the outskirts of dwarf galaxies. In cosmic voids, surveys scan these lonely galaxies, looking for stars with atmospheric spectra devoid of heavy elements. So far, none have been found. The search continues. Every new, deeper observation of void galaxies brings that possibility closer. This quest reframes the void. It's no longer just an architectural feature or a dark energy probe. It's an archaeological dig site. The sparse galaxies are like artifacts on the surface, but the real treasure is buried in the spaces between them. It's the undisturbed sediment of the cosmic dawn. Can we still find a pocket of the universe exactly as it was before the first chapter of its story was written? The voids offer our best chance, perhaps our last chance, to sample the primordial recipe, to taste the universe before it was cooked. In their deep quiet, they guard the memory of a time when everything was simple, raw, and waiting to begin. That search for pristine ingredients makes you wonder about our own place in the recipe. Whether the cosmic void we might be in was itself a necessary ingredient for life. This ninth mystery ties the architecture of emptiness directly to the possibility of existence. If our Milky Way is inside a local underdensity, a quiet suburb, that puts us in a uniquely stable environment. Astrobiologists talk about the galactic habitable zone, a region in a galaxy where conditions are right for life, not too close to the violent center, not too far out in the sparse outskirts. You can extend that idea to the scale of the entire cosmic web. A cosmic habitable zone. The dense knots of galaxy clusters are hostile places. They're cauldrons of intense radiation, frequent galactic collisions, constant gravitational turmoil. A planet there would face bombardment. Its atmosphere could be stripped by a nearby supernova. Its solar system could be destabilized by close encounters with other stars, or sterilized by a gamma-ray burst, a beam of energy from a dying star, which is far more common in those crowded stellar cities. A cosmic void offers shelter. The sparse population means fewer neighboring galaxies, fewer nearby supernova, a drastically lower chance of a catastrophic gamma-ray burst pointing at any one planetary system over billions of years. The gentle gravity lets planetary systems form and evolve in relative peace, orbits stable over eons. That provides the consistent, long-term conditions needed for chemistry to become biology. It's the difference between building a house of cards in a calm library and building it on the deck of a ship in a stormy sea. The void is the calm library. It offers the quiet and the time for complexity to assemble. This touches on the anthropic principle, the idea that the universe we observe must be compatible with observers. In its weakest form, it just notes a curious fact. We find ourselves in a place that allows for our existence. Our potential location in a void could be a specific, large-scale example. We are not in a random spot. We are in a spot that's been quiet and safe enough for nearly 5 billion years of unbroken evolution on our planet. To see the difference, consider the rate of sterilizing events. In the core of a massive galaxy cluster like Coma, a typical star might experience a nearby supernova or a galaxy merger every few 100 million years. Each event could reset the clock on any complex life. In a void, such catastrophic interludes might be separated by many billions of years, if they happen at all. It grants a continuity that seems essential. So you get a reflective question. Was cosmic emptiness a prerequisite for the complexity we see on Earth? Could the great voids, these deserts of darkness, actually be the fertile grounds for the most delicate flower in the universe, conscious life? It's a humbling connection. It suggests the largest structures, the tapestry of light and dark, aren't just a spectacle for us to observe. They may be the very foundation that made the observer possible. Our existence might be woven into the silent fabric of the void. Those lonely galaxies end up fading. Their light just goes out. The voids keep swelling, they become the main thing you see, and the galaxies stuck inside them change slowly. They're the last things left in a universe that's emptying out. It starts with cosmic isolation. The expansion, the dark energy, it doesn't just push things apart. It cuts the connections. First, the gravitational ties. A galaxy on one side of a void will find the void itself is expanding faster than gravity can cross it. So there's no pull left, no future merger. The galaxy is alone gravitationally. Then the information ties are cut. Light from any other galaxy, from anything outside its own little group, will eventually stop arriving. Its future light cone shrinks down until it only contains itself. Everything else moves beyond an event horizon. It vanishes from the sky, from any chance of being known. Inside that isolated island, the galaxy's own evolution runs its final course. The fuel for new stars, the cool hydrogen gas, gets used up or heated. There's no fresh gas falling in from outside, because the space between galaxies is receding too fast. So star formation stops permanently. All the stars age together. The big, hot blue stars die first in supernova, leaving neutron stars and black holes. The medium stars, like our Sun, run out of fuel, swell into red giants, then shed their layers, leaving white dwarfs. The smallest, reddest stars burn so slowly they last for trillions of years. Over time, the galaxy's color shifts from any blue left to a deep, uniform crimson. It becomes a fossil galaxy, a silent collection of old red dwarfs, white dwarfs, neutron stars, and black holes orbiting in the dark. Long-term simulations running the clock forward hundreds of billions of years show this clearly. Take a galaxy like Leo T. It's a tiny, gas-rich dwarf near us, already in a low-density spot. Right now, it's a modest star former. But in the far future, as its local void expands and swallows everything around it, its gas will be used up or stripped away by the gentle pressure of the void's hot plasma. Its star formation will sputter out. Its bright young stars will fade. What's left is a dark, diffuse halo of old stars, so faint and red it'd be almost invisible to anyone not already inside it. It becomes the last fading ember in an ocean of night. That leads to a question. Could any advanced awareness, any civilization that arises in one of these final islands, ever know about the rest of creation? For them, the cosmological story ends early. Their observable universe shrinks to just their own galaxy. The cosmic microwave background redshifts until it's undetectable. The redshift of all other galaxies approaches infinity, wiping them from view. The evidence for the Big Bang, the expanding universe, the cosmic web, all of it vanishes. Their cosmos is a single, static galaxy in an eternal black void. They'd have no way to figure out the grand, dynamic history we're piecing together now. They'd live in a universe that forgot its own past. That's the loneliness written into the far future. The voids, which started as subtle seeds and grew into the dominant structure, will finally become the only landscape. The last islands of light, the fossil galaxies, will themselves eventually dim as their longest-lived stars finally flicker out. The closure is profound. The great cosmic voids, which we study now as physics labs and windows to the dawn of time, are also the gentle architects of a final, silent peace. They're not destroyers. They're quiet ushers. They guide the universe from a state of brilliant, chaotic connection to one of serene, isolated rest. In their ultimate expansion lies the end of all stories, including the story of the light they once helped to arrange. The future of those fossil galaxies is written by the same rules we can read in the emptiness today. All the subtle orders we've found, the aligned spins, the dark scaffolds, the imprints on the ancient light, they aren't separate curiosities. They're chapters in one story, a coherent story, and it makes the cosmic void the most powerful laboratory we have. This order inside the great nothings, it's a multi-messenger testbed. It probes the whole standard model of cosmology, and it opens windows to what might lie beyond it. Experts point to a crucial symmetry. Galaxy clusters show us the universe in its most dense, violent, chaotic state. That's the cosmic extreme. Voids show us the opposite. They reveal the universe in its most gentle, quiet, foundational state. If clusters are a roaring concert, voids are the silent spaces between the notes. You need both to understand the music. The violent physics of clusters is complex. It's tangled with feedback from stars and black holes. but the gentle physics of a void is clean. It's dominated by the pure, large-scale forces: gravity, dark matter, dark energy. In the void, the signal isn't drowned out by the noise. So what does this quiet laboratory tell us? It starts with inflation. The nested hierarchy of voids, their size distribution, it's a fossil record. A fossil of the quantum fluctuations from the universe's first fraction of a second. The pattern of emptiness today is a direct imprint of that primordial expansion. Then there's dark matter. The serene motion of galaxies within voids, the way they trace the contours of an invisible landscape, that puts the strictest constraints on dark matter's properties. Is it cold or warm? The dynamics of emptiness help provide the answer. Dark energy's fingerprint is even clearer. The swelling rate of voids, how quickly they expand faster than the universe itself, that's a direct gauge. A gauge of dark energy's strength and constancy. And for normal matter, the baryonic physics, voids are where we finally found the missing atoms, hiding in the million-degree fog of the warm-hot intergalactic medium. They show us how gas behaves in its most diffuse, undisturbed state. The true power comes from combination. Studying nothing gives the cleanest signal, but using all the signals together breaks degeneracies. Imagine trying to solve a puzzle with pieces that look similar. One measurement of the universe's expansion might be consistent with several different combinations of dark matter and dark energy. But when you add a second, independent measurement like the statistical pattern of void shapes, many of those combinations become impossible. Add a third, like the void CMB correlation, and the picture sharpens dramatically. Take void shapes and their growth history together. The shape of a void, whether it's spherical or elongated, tells us about the initial conditions and the tidal forces from the surrounding web. The rate at which that void has swollen over billions of years tells us about dark energy. By measuring both for thousands of voids, cosmologists can separate the influence of the universe's initial setup from the influence of its accelerating fate. It's like having two different keys to unlock the same safe. This synthesis reframes everything. What if the great voids aren't the backdrop, but central characters in the cosmic story? Their subtle order is the universe's way of revealing its deepest rules in the quietest possible room. Every aligned galaxy, every faint magnetic whisper, every cold spot on the CMB is a piece of evidence. Evidence that to understand the cosmos, we must listen as carefully to its silences as we do to its explosions. The emptiness is speaking, and its message rewrites our place in the narrative. Not as observers of a distant spectacle, but as inhabitants of a quiet suburb, in a vast, structured, deeply ordered expanse of darkness and light. From the quietest quantum beginnings to the final stillness of galaxies, moving through cosmic voids changes what we think emptiness means. They aren't blank. They have structure, they hold information, they make you question what nothing really is. The order we've seen, the way isolated galaxies spin in alignment, the dark frameworks of gravity, the cold marks on the oldest light, it all points to a coherent universe. A connected one. On the largest scales, the emptiest regions keep the cleanest records. So these voids aren't just empty, they're essential, they aren't the backdrop. They're central. From their quantum origins right after the Big Bang to becoming the universe's last quiet places, voids are active. They are pristine labs. They are fossilized sound waves. They measure dark energy. They hold atoms we've been missing, and they might even tell us about dark matter. To understand where we came from, what we're made of, and where we're going, we have to learn to read the dark. It's a reminder. To see the universe's biggest wonders, sometimes you have to look away from the bright lights. You have to look into the deep, structured darkness between them. The mystery is written there, in the subtle architecture of what's missing. It's an invitation to look up,